Hello everyone. So, in today's class we will solve natural convection over a vertical flat plate using integral method. You have already learnt this integral method in module 4 lecture 1 we have derived the momentum integral equation, and in module 4 lecture 2 we have derived the energy integral equation. So, please refer these derivations. In today's class we will use the momentum integral equation and energy integral equation with some modification, because we have a buoyancy term in the boundary layer equations for natural convection flow, and we will solve for the unknown variables delta. So, if you remember, in forced convection we have two unknowns, one is hydrodynamic boundary layer thickness delta and thermal boundary layer thickness delta T, and we had two integral equations and we solved for delta and delta T. In natural convection we will assume that delta is equal to delta T. For this we will solve these equations and we will find the unknown variable delta and another unknown variable velocity profile. Although we are assuming that delta is equal to delta T, but later we will show that the solutions whatever we will be deriving using this integral analysis, it will be valid for wide range of Prandtl number. So, let us consider natural convection over a vertical flat plate. The plate is maintained at uniform wall temperature T w and the quiescent medium temperature is T infinity, and that is also maintained at constant temperature. Here we have these assumptions: two dimensional steady laminar flow with constant properties. We have Boussinesq approximation valid and T w is constant, T infinity is constant, and we are neglecting the viscous dissipation. So, in this integral solution we will assume delta is equal to delta T, that means Prandtl number is almost 1, but we will write the solution in terms of Prandtl number and we will show that the solution is reasonably valid for wide range of Prandtl number. So, first let us write the boundary layer equations for natural convection over a flat plate. So, we have already derived these equations, boundary layer equations. So, continuity equation, okay. The momentum equation is u del v by del x plus v del v by del y is equal to nu del 2 v by del x square plus g beta t minus t infinity. So, in this case, okay, x is perpendicular to the wall and y is along the vertical wall, and energy equation u del t by del x plus v del t by del y is equal to alpha del 2 t by del x square. Okay. So, you refer module 4 lecture 1 and 2 for derivation of these integral equation. So, if you derive you will get momentum integral equation as so using the continuity equation you can derive the momentum integral equation from this momentum equation as d of dy 0 to delta rho v square dx will be equal to minus mu del v by del x at x equal to 0. What does it mean? It is the wall shear stress, right, and we have another term, that is your buoyancy term, which was not there for forced convection. Okay. So, that we will write in integral form 0 to delta, okay, rho g beta t minus T infinity into dx. Okay. And energy integral equation okay, you can write as d of dy 0 to delta t v t minus T infinity dx is equal to minus alpha del t by del x at x equal to 0. So, you can see minus k del t by del x at x equal to 0 will give you wall heat flux, okay. And here alpha is thermal diffusivity. So, now we will assume delta is equal to delta t. So, here the integral, okay, we will integrate up to delta. Okay. We will solve for two unknowns. Okay. One is delta, which is function of y, and another is unknown velocity profile. Okay. So, some will derive later, some velocity v naught. So, which will be function of y. So, these are the two unknowns. We will use these two integral equations and we will solve for delta y and v naught. So, what is the next step while using the integral method? So, you have to assume the velocity profile and temperature profile. Then once you get the velocity and temperature profile, you have to invoke those in the integral equations. So, first let us see what is the assumed velocity profile. Okay. So, we will use here 4th degree polynomial for velocity. Okay. So, we will use v, which is function of x and y, is equal to coefficient a naught, which is function of y, a 1 y x plus a 2 y x square plus a 3 y x cube. So, we have to find these coefficients a naught, a 1, a 2 and a 3. So, there are 4 coefficients. So, how many boundary conditions do we need? So, we need 4 boundary conditions. 2 boundary condition you know easily. One is the wall, you have velocity 0, okay, at x tends to infinity you have velocity 0, and also at x tends to infinity you have velocity gradient is 0, because it is a quiescent medium. Another boundary condition you have to derive, okay. So, from the momentum equation. So, that is the derived boundary condition. These already we have discussed in module 4. So, boundary conditions at x equal to 0 you have b is equal to 0, at x equal to delta you have b is equal to 0, also the velocity gradient is 0 because you have a quiescent medium. So, del b by del x is 0, and another boundary condition that is derived from the momentum equation. So, at x equal to 0 you can write del 2 v by del x square is equal to minus g beta by nu t w minus t infinity. So, in the momentum equation the inertia term will become 0 because u v are 0. So, this is your viscous term, okay, and at wall you have t is equal to t w. So, you can write del 2 v by del x square is equal to the buoyancy term divided by the nu. So, if you invoke this boundary condition and find the coefficients, you will get a naught is equal to 0, A1 is equal to G beta T w minus T infinity delta by 4 nu, A2 is equal to minus G beta T w minus T infinity divided by twice nu, and A3 is equal to G beta T w minus T infinity divided by 4 nu delta. Okay. So, now these coefficient if you substitute in the assumed velocity profile, then you will get the velocity profile. So, if you see substituting the values of the coefficient, we get. Okay. So, if you substitute it here, so you will get the velocity profile as V is equal to G beta T w minus T infinity divided by 4 nu delta x 1 minus 2 x by delta plus x square by delta square. Okay. If you rearrange it, you will get G beta T w minus T infinity delta square divided by 4 nu x by delta 1 minus x by delta square. So, you can see the first term in the right hand side in the inside the bracket. Okay. So, this term can form the characteristic velocity. Okay. Now, we will say that it is the characteristic velocity and V naught, okay, which is function of y, and this is to be found from the solution. So, this is another unknown G beta T w minus T infinity delta square by 4 nu. So, you can see delta is function of y. So, V naught is also function of y. So, this is the second unknown. First unknown is delta we have to find, and another unknown V naught we have to find. Okay. So, now you can write the velocity profile as V by V naught, okay, is equal to x by delta 1 minus x by delta square. Okay. Now, you know the velocity profile, assumed velocity profile, and that from that we can find the maximum velocity location. So, at which location you will get the maximum velocity. So, if you take the derivative of velocity v, then make it 0, then you will be able to find at which location you will get the maximum velocity, at which x location, right. So, the maximum velocity and its position distance from the wall in x direction at any y can be obtained as, so we can write del v by del x is equal to 0. So, that means del of del x v naught, okay, x by delta 1 minus 2 x by delta plus x square by delta square is equal to 0. So, you see v naught is function of y and delta is also function of y. So, you can take it outside the derivative. So, you can write del of del x x minus 2 x square by delta square plus x cube by delta cube is equal to 0, okay, because V naught is function of y and delta is function of y, right. And from here if you see, so you will get 1 minus 4 x by delta plus 3 x square by delta square is equal to 0. If you rearrange it, you will get delta square minus 4 delta x plus 3 x square is equal to 0, and you will get delta minus x delta minus 3 x is equal to 0. You can see x equal to delta, you have velocity 0. So, there will not be maximum velocity. So, x not equal to delta, because at x equal to delta you have v is equal to 0, right. So, you have delta minus 3 x equal to 0, that means x equal to delta by 3. Okay. So, you can see at x equal to delta by 3 you will get the maximum velocity. Okay. So, therefore, v is maximum at x equal to delta by 3, and its value if you find, it will be v max. Okay. After simplification I am writing 4 by 27 g beta t w minus t infinity delta square by 4 nu. So, we have found the velocity distribution. Now, let us find the temperature profile, okay, assume temperature profile. So, for that also we will use a third degree polynomial. Okay. So, assumed temperature profile we will use third degree polynomial. Okay. So, if it is so, then you can write t as function of x y is equal to coefficient b naught, which is function of y, plus b 1 x plus b 2 x square. So, now you need 3 boundary conditions to find the 3 unknowns b naught, b 1 and b 2. So, you know at wall you have temperature T w, at x tends to infinity you have temperature T infinity, which is the quiescent fluid temperature, as well as x tends to infinity your temperature gradient is 0. So, you can write boundary conditions, okay, at x equal to 0 you have T is equal to T w, at x tends to infinity you have T is equal to T infinity, and also the temperature gradient is 0. So, applying boundary conditions, okay, and solving for the coefficients, we get, applying boundary conditions and solving for coefficients, okay, we get b 0 is equal to T w, b 1 is equal to minus 2 T w minus T infinity by delta, and b 2 is T w minus T infinity by delta square. Okay. So, if you put these values in the assumed temperature profile, then you will get T x y is equal to T infinity plus T w minus T infinity 1 minus x by delta square. So, now we have assumed the velocity profile as well as the temperature profile. Now, we want to put these profiles into the integral equations. Okay. So, because you have the momentum equation where you have temperature profile as well as you have the velocity profile. So, in the momentum integral equation you need the temperature profile as well as the velocity profile. Okay. So, if you put there, so you have momentum integral equation so that is your d of dy 0 to delta rho v square dx is equal to minus mu del v by del x at x equal to 0 plus 0 to delta rho g beta t minus t infinity dx. Okay. Now, put the velocity profile and temperature profile. So, you have v is equal to v naught x by delta 1 minus x by delta square, okay. And temperature profile T is equal to T w plus T w minus T infinity into 1 minus x by delta square. Okay. So, here you can see you have T minus T infinity. So, if you rearrange it, so sorry, it is T infinity. So, T minus T infinity will be T w minus T infinity into 1 minus x by delta square, and this equation if you divide both side by rho, then if you rearrange you will get d of dy 0 to delta v naught square by delta square x square 1 minus x by delta to the power 4 dx is equal to minus nu v naught by delta. So, if you find del v by del x from here, then you will at x equal to 0 you will get v naught by delta. Okay. So, del v by del x at x equal to 0, okay. You find it, you will get it as v naught by delta, okay. And plus the buoyancy term. So, if you put the buoyancy term, so you will get g beta, we have divided by rho already, T w minus T infinity integral 0 to delta 1 minus x by delta square dx. Okay. So, now evaluating the integrals and rearranging, okay, you will get 1 by 105 d of dy v naught square delta is equal to the buoyancy term. If you write first, then it will be 1 by 3 g beta T w minus T infinity into delta minus nu v naught by delta. Okay. Now, similarly, you put the value of temperature profile in the energy integral equation. So, energy integral equation, if you remember, okay. So, it was d of dy, and here we are integrating 0 to delta, because we have assumed that delta is equal to delta t. So, v into t minus t infinity dx is equal to minus alpha del t by del x at x equal to 0. So, put the velocity profile and the temperature profile here. So, you will get d of dy v naught by delta T w minus T infinity 0 to delta x into 1 minus x by delta to the power 4 dx is equal to minus alpha T w minus T infinity, and del t by del x at x equal to 0. If you find del t by del x at x equal to 0, So, from here you can see it will be minus 2 by delta into T w minus T infinity. Okay. So, from here you can see, so it will be minus 2 by delta. So, just rearranging, okay, you will get 1 by 60 d of dy v naught delta is equal to alpha by delta. Okay, so, you can see we have got first order ordinary differential equation. So, this is one equation and this is another equation, these are first order ordinary differential equation, and we need to find V naught and delta from here. So, we assume the solution for two dependent variables of the form V naught, okay, which is function of y. So, we will use a y to the power m because it is function of y, and delta we will assume as b y to the power n, where a, b, m, n, okay, are constants. Okay. So, now if you put these values in the ordinary differential equation. So, for momentum equation we got this ordinary differential equation and find the value of a, b and m and n. So, you will get v naught square delta is equal to 1 by 3 g beta T w minus T infinity delta minus nu V naught by delta. Okay. So, put the V naught and delta expression here. So, you will get V naught square delta as a square b y to the power 2 m plus n. Okay. So, if you take the derivative with respect to y, then you will get twice m plus n by 105 a square b, these are constants. So, and you will get y 2 m plus n minus 1. Okay. The boundary term g beta T w minus T infinity. So, delta, okay, so it will be b y to the power n minus v naught by delta. Okay. So, it will be a by b nu y to the power m minus n. Okay. And another ordinary differential equation we have. So, that is your one by 60 d of dy v naught into delta is equal to alpha by delta. So, if you see v naught into delta will be a b y to the power m plus n. So, you can take the derivative with respect to y. So, you will get m plus n divided by 60 a b y to the power m plus n minus 1 is equal to alpha by b y to the power minus n. So, you can see we have this equation and we have this equation, and to satisfy the equations at all values of y, the exponents of y in each term must be identical. Okay. So, to satisfy the equations at all values of y, the exponents of y in each term must be identical. Okay. So, if it is so, then you can write twice m plus n minus 1 is equal to n, and also you can write n is equal to m minus n, and you can write m plus n minus 1 is equal to minus n. Okay. So, from here you can find, okay. So, you can see from here you can find m is equal to 2 n, and if you put it here, so you will get n is equal to 1 by 4 and m is equal to half. Okay. So, now you can see we have found the exponent m and m is equal to half and n is equal to 1 by 4. So, now we have to find other two constants, that is a and b. Okay. So, now these exponents you put in those equations, after simplification you will get 1 by 84 a square b is equal to 1 by 3 g beta t w minus t infinity b minus a by b nu, and if you simplify it. So, you will get, so this is one equation you will get, and another equation you will get 1 by 80 a b is equal to alpha by b. So, what we are doing? So, we are substituting the value of m and n in this equation, okay, and in this equation. Okay. So, from the first equation you are getting this, and from the second equation you are getting this. So, from here you can write a is equal to 80 alpha by b square, okay, and this you substitute it in the first equation. Okay. So, what you will get? So, substitute the value of a in the first equation, top equation. Okay. So, what you will get? 1 by 84 80 alpha by b square b is equal to 1 by 3 g beta t w minus t infinity into b minus, now value of a you write 80 alpha by b square into nu by beta. Okay. So, what you do? You multiply both side by b cube, multiply both side by b cube. So, if you rearrange it, so you will get 6400 divided by 84 alpha square is equal to 1 by 3 g beta t w minus t infinity b to the power 4 minus 80 alpha nu. So, from here you will find that b to the power 4. Okay. So, if you see it will come almost 76.19. Okay. So, we are writing 76.19. So, b to the power 4 you will get 80 alpha square nu by alpha after rearrangement. Okay. 76.19 divided by 80 3 nu square divided by g beta t w minus t infinity into 1 by nu square. Okay. After rearrangement you will get this, and this 76.19 by 80 we will write as 20 by 21. Okay. So, you can write the value of b now as 3.93 Prandtl number to the power half, Prandtl number to the power minus half, Prandtl number 20 by 21 to the power 1 by 4 g beta t w minus t infinity divided by nu square to the power minus 1 by 4. Okay. So, now you will be able to find the value of a as 80 alpha by b square. Okay. So, b value you substitute and rearrange, you will get as 5.17 nu Prandtl number plus 20 by 21 to the power minus half g beta T w minus T infinity divided by nu square to the power half. Okay. So, now you know the value of A and B, m and n. So, you will be able to write the velocity profile and the boundary layer thickness delta. We have m is equal to half, n is equal to 1 by 4 and the expression of A B. So, you will be able to find the velocity V naught as A y to the power m. So, if you put all these values and you will get 5.17 nu Prandtl number plus 20 by 21 to the power minus half g beta T w minus T infinity divided by nu square to the power half and y to the power m. So, y to the power half. Okay. So, now what we will do, you can see if we put inside here y cube, then it will represent the Grashof number, right, g beta delta t y cube by nu square. So, that will give you the non-dimensional number Grashof number. So, we will put inside y cube. So, it will be and we will subtract from here. So, after rearrangement you will get V naught is equal to 5.17 nu by y Prandtl number plus 20 by 21 to the power minus half Grashof number to the power half. Okay, where Grashof number we have the expression g beta T w minus T infinity y cube by nu square. Okay. And we have delta as b y to the power n. Okay. So, you know b as 3.93 Prandtl number to the power half Prandtl number plus 20 by 21 to the power 1 by 4 g beta T w minus T infinity divided by nu square to the power minus 1 by 4 y to the power 1 by 4. Okay. And similar way here we will also put inside y cube and we will rearrange and we will get delta by y as 3.93, sorry, this is minus, okay, Prandtl number to the power minus half. So, Prandtl number to the power minus half Prandtl number plus 20 by 21 to the power 1 by 4 and you can see you will get Grashof number to the power minus 1 by 4 and we can write delta by y. Okay. So, Prandtl number and into Grashof number, what it will give? It will give Rayleigh number. Okay. So, Rayleigh number is your Grashof number into Prandtl number. Okay. So, if you write it, you will get 3.93. Okay. So, you see it is Prandtl number to the power minus half, here you need Prandtl number to the power minus 1 by 4. Okay. So, you have to divide by Prandtl number to the power 1 by 4 here to write Rayleigh number. So, you will get here, so you will get 1 plus 20 by 21 into 1 by Prandtl number to the power 1 by 4 Rayleigh number to the power minus 1 by 4. So, you can see this equation will give you the boundary layer thickness, okay, along y. So, the above equation gives the variation of delta along y. Okay. And if you remember, we have assumed delta is equal to delta t but we have retained the expression in terms of Prandtl number. Okay. So, now we will find the heat transfer parameters. So, we will find the local heat flux, then heat transfer coefficient and the Nusselt number. So, let us write the local heat flux from the wall. Okay. So, we have q double prime w is equal to minus k del T by del x at x equal to 0, okay. And we have shown that you will get minus k. So, this del T by del x at x equal to 0, okay, you will get as minus 2 by delta into T w minus T infinity, right. So, this will get twice k by delta T w minus T infinity. So, the local heat transfer coefficient you can write H is equal to q double prime w by T w minus T infinity. So, this is from Newton's law of cooling. So, you will get, you see from here, twice k by delta. Okay. So, delta expression you know. So, if you put the value, then you will get H as twice k by y 1 by 3.93, 20 by 21, 1 by Prandtl number plus 1 to the power minus 1 by 4 Rayleigh number to the power 1 by 4. So, this we are writing from this expression. So, you can see we have delta by y. Okay. So, this expression, from this expression we are writing the value of heat transfer coefficient. Now, you can write the local Nusselt number. Okay. So, you will get h y by k. So, it will be 2 y by delta. Okay. From this expression you can see h y by k, you can write 2 y by delta. So, if you put this value of delta by y, then you will get 0.508, 20 by 21, 1 by Prandtl number plus 1 to the power minus 1 by 4 Rayleigh number to the power 1 by 4. Okay. So, now the average heat transfer coefficient, the average heat transfer coefficient you can write as h bar is equal to 1 by h integral 0 to h into dy, okay, and put the values, then you will get 0.508 k by h, 20 by 21, 1 by Prandtl number plus 1 to the power minus 1 by 4 g beta T w minus T infinity divided by alpha nu to the power 1 by 4 and integral 0 to h y to the power minus 1 by 4 dy. Okay. So, if you integrate it and rearrange, you will get h bar is equal to 4 by 3 0.508 k by h, 20 by 21, 1 by Prandtl number plus 1 to the power minus 1 by 4 R A H to the power 1 by 4. Okay. So, now Nusselt number, average Nusselt number you can write is equal to h bar h by k. So, you will get 4 by 3 point into 0.508 20 by 21, 1 by Prandtl number plus 1 to the power minus 1 by 4 RAH to the power 1 by 4. From here you can see the average Nusselt number will be equal to 4 by 3 times the local Nusselt number at y is equal to h, right. So, from here you can see that your average Nusselt number will be 4 by 3 local Nusselt number at y is equal to h. So, now we will discuss about two limiting cases. Okay. One is Prandtl number tends to 0 and another is Prandtl number tends to infinity. Now, let us discuss about two limiting cases when Prandtl number tends to 0 and Prandtl number tends to infinity. You know, when Prandtl number is much less than 1, your Nusselt number will be function of Rayleigh number and Prandtl number, and when Prandtl number tends to infinity, that means when you have a high Prandtl number fluids, then your Nusselt number will be function of only Rayleigh number. So, already we have found the value of delta by y. First let us write that expression. So, delta by y is equal to 3.93 20 by 21 plus Prandtl number to the power 1 by 4 Rayleigh number into Prandtl number to the power minus 1 by 4. So, now consider the limiting case for Prandtl number tends to 0. So, if Prandtl number tends to 0, you can see this term you can put 0. So, you can write delta by y is equal to 3.93 20 by 21 to the power 1 by 4 Rayleigh number Prandtl number to the power minus 1 by 4. So, from here now you can write the expression of Nusselt number. You know Nusselt number is 2 into y by delta, right. So, this expression if you put local Nusselt number, now you can write from the integral solution okay, after rearranging you will get 0.515 Rayleigh number into Prandtl number to the power 1 by 4. And if you remember this Nusselt number from the exact solution, okay, from the similarity solution we have written as 0.6 Rayleigh number into Prandtl number to the power 1 by 4. Okay. And for Prandtl number tends to infinity, okay, another limiting case, we can write the expression of delta by x as 3.93 20 by 21 1 by Prandtl number plus 1 to the power 1 by 4 Rayleigh number to the power minus 1 by 4. Okay. So, as Prandtl number tends to infinity, you can see this term will become 0 because 1 by Prandtl number is there. So, we can write delta by x is equal to 3.93 Rayleigh number to the power minus 1 by 4. Sorry, this is delta by y. Okay, this is delta by y. So, obviously, now Nusselt number you can write okay, twice y by delta. So, from integral solution, okay, if you write it will get 0.508 Rayleigh number to the power 1 by 4, and you can see for high Prandtl number fluids it depends on only Rayleigh number. And if you remember, we have written the exact solution from the similarity solution as 0.503 Rayleigh number to the power 1 by 4. Okay. So, you can see here this is almost 1% variation. Okay. For Prandtl number tends to infinity, there is a 1% variation, and maximum variation occurs as Prandtl number tends to 0. So, this around 14% you will get. So, in these two limiting cases you can see this variation of this Nusselt number between the integral solution and the exact solution varies between 1% to 14%. So, you can see although we have assumed that delta of the order of delta t, but still this gives a reasonable good solution for the different Prandtl numbers. So, the observation whatever we have made, you can see the error ranges from 1% for Prandtl number tends to infinity to 14% for Prandtl number tends to 0, and although the integral solution is based on the assumption that delta is equal to delta t, the solution is reasonable accurate for a wide range of Prandtl numbers. So, in today's class we have solved the boundary layer equations using integral method. So, first we integrated the momentum equation and the energy equation, and we have written the momentum integral equation and energy integral equation. Then we have assumed the velocity profile and temperature profile, and invoking those expression in the integral equation, we have written two ordinary differential equations. Then we have written the expression for delta and V naught, and we have put in the ordinary differential equation, and we have found the value of delta by y, and from there we have found the heat transfer parameters like heat transfer coefficient, Nusselt number, and we have also shown the two limiting cases where Prandtl number tends to 0 and Prandtl number tends to infinity, and we have shown that in these limiting cases your error of integral solution compared to the exact solution varies between 1% to 14%. Thank you.